Today we're going to do 1518. Tomorrow we'll do it as well. So hopefully half and half would be a nice way to get through it. So what section 15.8 is about is triple integrals, and that is triple integrals using spherical coordinates. And we had a picture yesterday, we had a picture on Friday that basically tells you how to locate an object in 3D space. And I used the example from the book, although it wasn't particularly nice. So what you do is, if you want to imagine that you've got a point over here, I'll call it P. In the good old-fashioned XYZ coordinate, it also can be written down in rho theta phi in polar coordinates. So you imagine this point here, we'll use that one. So what you do is you go theta degrees in that direction, and then you go, it's kind of hard to imagine it, but you go like this and you go up here, and this going up angle is called phi. And then you tell people the distance along that angle, rho. So this is basically, you go this way, that away, and then shoot off. And on 2D paper, it never looks good, but that's essentially what we have. So why are triple coordinates or spherical coordinates and triple integrals so helpful? If the region, do you know, they have a region here, which they can call E. I think they've called it R, and in some places they've also called it D, but whatever letter of the alphabet they use. If that region is part of a sphere, or at least spherical, then it's very often easier math to find a triple integral of it, instead of using XYZ, to convert it into the spherical one. And I double checked, because that's something I always forget. That guy there is the extra little bit that you need to always have in your thing. You remember like the r d theta thing, right? That extra r. This is rho squared sine phi, and then you've got your three variables. Now, to be able to do a proper triple integral, what we need is conversions. So every x turns into this, every y turns into this, and every z turns into this. We also have restrictions on when you do a sphere or part of a sphere. I think they call it a ball. And I think all a ball means is that it's not just the surface of the sphere, it means the whole, like all the points inside as well. So if you wonder what a ball is, that's all it is. It's really just a sphere, but every point inside the sphere as well as the outside the surface. So back to this, rho has to be greater than 0. Phi has to go from 0 to pi, and you can imagine this is 0, and then you curve all the way down to the bottom, and 0 positive z to pi negative z. That basically covers everything that you need, so that's why that restriction is there. And the 0 to 2 pi, like imagine this is the xy plane. Theta basically lives in the xy plane, right? So if you go a big circle, you know, you need 0 to 2 pi to cover every point in 3D space. And another little guy, which basically says that x squared plus y squared plus z squared is equal to rho squared. So that's the package that we're going to use. I strongly suggest that you make sure that you have a copy of the key points here, you know, the key values, and that will allow us to essentially turn an XYZ triple integral into a rho theta phi triple integral, which tends to be much nicer and easier to do. That's the whole gist of why we do it. So this is question 1. And question 1 just wants us to take an equation in XYZ form and convert it into what would that look like if you were using polar coordinates, spherical coordinates. I could do the math of that, but I don't need to. Would you agree that's just all the points whose rho value is 5? Because isn't that the surface of a sphere, radius 5? On the other hand, if you muck about with stuff, like this guy, and you wanted to write down what that expression would look like in rho, phi, and theta, because can you imagine there was going to be like a triple integral of this guy, right? Then you need to be able to do that, right? So what it's basically just a plug and chug. X squared gets replaced by that fella. Take away y squared, which gets replaced, by that fella. Take away z squared, and the whole thing's equals 1. So what do I get? I get rho squared, sine squared, cos squared. Take away rho squared, sine squared, sine squared. Take away rho squared, cos squared equals 1. Now, it might be that that's as good as that's ever going to be. But if it is possible, and most of the time it should be, this guy here needs to be simplified. Any suggestions about what I might do?
You could take a rho squared.
Okay, good choice. And the answer is yes, you should.
And then doesn't the sine squared cosine squared go to 1?
So you combine these two guys together?
Different angle.
So
Multiplied. So
okay, I was wondering what I thought you were saying, and that's why I was about to agree with you, is that forget about this guy at the end, him. Not going to do anything with him. But I can do some with these two guys. Can you see anything I can do with these two guys?
yeah, factor out the sine squared phi.
And that leaves me with that, which might not look like much of an improvement, but you can in fact do a little bit. Do you recognize cos squared take away sine squared? Do you recognize cos squared take away sine squared? Because it is something.
It's cosine of 2 theta.
Now, one of the reasons, forget about the equals 1 part, but one of the reasons you want to be able to do this, if this thing is going to end up being integrated, would you agree it's a lot less work if you can make this as small as possible? And then the integration process should go along much smoother. If you leave something like this, you're just asking for trouble later on when you have to do the integration part. So it's a good skill to be able to take an expression and to simplify it as much as possible. Are we good?
Is the sine phi supposed to be sine squared?
Yes.
It is.
Yes. Are we good? Put that there for a second. In this question, we have a solid that lies above the cone. Z equals the square root of x squared plus y squared. And it ends up below the sphere, x squared plus y squared plus z squared equals z. We're being asked to write, I would call it the limits. So we need to figure out those three guys. Okay, so let's see how this fella and this fella might interact, and we're going to use these guys to help us. So I'm going to start with what this fella would look like if he was in polar form. Because once I convert him to polar form, that should give me the limits of integration of what, well, whatever it ends up being. I happen to know what it's going to be, but we don't yet. So in this case, we have a z equals an x squared plus a y squared, and z is the row of cosine phi, and it's going to be the square root of this guy squared plus this guy squared. I'm going to do the squaring as I write it. Z is this guy, this is x squared, plus this is y squared. Can you pull out a rho squared? Yup. Can you pull out a sine squared? Yup. If you do that, what you're left with is cos squared theta plus sine squared theta. Well, what do you get here? Well, isn't that 1? And isn't the square of that that guy? And if I divide both sides by r cosine phi, you get 1 is equal to that. But the rows cancel, and you're left with that. I'm taking this slowly. Which means you are left with this. So the tan of phi is 1. Doesn't that make that a number? What angle is phi? What
Pi over
angle has
4.
it? Yeah. Now, technically speaking, there's lots of right answers that you could be, but in spherical coordinates, doesn't it have to be in the first or second quadrant? And isn't this the first quadrant answer? So boom. That means that I can now put a limit on what phi can be. Are we happy about how I got that fella? Right. Now I'm going to take this second thing and we are going to figure out what does this guy look like when he is turned into polar. Well, that's going to involve a fair chunk of work here. This guy squared is r squared. This fella, this one. Why am I doing this? What I just did would eventually work, but I've found a much easier way of doing this.
Yeah, doesn't it all add up to p squared?
Yeah, isn't that just rho squared?
Oh.
Now, z is rho cosine phi. Now, eventually this would have turned into that, right? But you know, why do I need to do 10 minutes work when I know the answer right away? So this is r squared, rho squared, and this is rho cosine theta. So far, so good. Now, if you bring them together, and you pull out rho as a common factor, don't you get rho equals 0 and rho equals cosine phi, which means that we now have restrictions on what rho can be. So the question we were asked to do was to take these regions inside this and outside that and describe them in terms of what the constraints on your triple integral would be. And we now know that rho should be that. We now know that phi should be that. And now I have to figure out what theta can be. In the two guys that we used, was theta even mentioned? No. Does not mean that theta has no restrictions. Right? There's nothing to make it bigger or less than something else. And since it has no restrictions, unless you're told otherwise, you'll assume that it's 0 to 2 pi. So this would be the triple integral limits of integration. If you were trying to find the volume of a shape from here to here, for instance. Are we okay? We're happy with what I just did? Going to move on then. So there's a version of question 4. Suppose I give you the integral from 0 to pi upon 4, the integral from 0 to pi upon 2, and the integral from 0 to 1 of rho squared sine phi d rho d theta d phi. So there is a already basically triple integral using spherical coordinate system. Is this variable separable?
Yes.
Now, these guys do not have labels telling you who they are. But since that's the last one, doesn't that tell me that phi is from 0 to pi upon 4? Since this is the middle one, won't that tell me theta is 0 to pi upon 2? And this one here is the first one, so isn't that telling me the rho guys? I think it much easier to know that, right? Now, can you see how I figured it out from position? Right, inside out. Now, let's separate them out then. We have a sine phi, d phi, and that's going to go from 0 to pi upon 4. And theta is going to 0 to pi upon 2. Anything happening with theta? Nope, so you get 1. And then the rho is going to go from 1 to 0 to 1 of rho squared d rho. Are we comfortable with the variable separable and the limits of integration for each? I guess I should finish this one. I probably won't do most of these questions to the end, but just because this is the first one. Right, if you integrate this guy, you get negative cosine phi from theta equals 0 to theta equals pi upon 4. For this middle one, you just get, to heck with it. Since that's 1, can't I just tell you the answer's pi upon 2? You're pretty obvious why that is. And this one is 1/3 rho cubed from rho equals 0 to rho equals 1. Okay, that's a bit messy. Negative the cosine of pi upon 4. Take away negative is add. Add the cosine is 0. So that's what that one's going to be. This is still pi upon 2. And this is going to be a third. That's 1 and that's root 2 over 2. And that's going to get me pi over 6. So that would be the final answer, I hope. We happy? Pi over that gets you this, and that's 1, and that's this guy, and that's what you get there. So far, so good. Okay, let's move on then. This is a version of question 5. We're being asked to do a triple integral over a ball, which is just a sphere. And the function is going to be x squared plus y squared plus z squared squared dv. And the ball is a radius of 2. Okay. Now, if you want to describe the limits of integration for a typical sphere, you're going to do rho equals 0 to 2. That takes care of that. Since it's an entire sphere, theta, well, I'm doing it as theta. So theta is 0 to 2 pi, and phi only goes 0 to pi. Are you comfortable with these? Are basically pretty standard. Those two, for instance, are pretty much always the same. And doesn't this one just depend on how big the sphere is? Now, x squared plus y squared plus z squared gets replaced by a rho squared, and so rho squared squared. And the dv gets replaced by all of this. So it's going to be rho squared sine phi, a d rho, a d theta, and a d phi. Okay, I want to save some time here. Is this going to be a variable separable story?
Yes.
Right, so let's see if I can bring them up. There's no indication of any thetas here, so that's going to be, oh, sorry, phi. There is an indication of phi, so that's going to be a sine of phi from 0 to pi. Anything else? No. There's no indication of anything happening in the theta world. So that's just going to be a 1. And 2, 4, 6. So you're going to get a 6 of them from 0 to 2 d rho. Are you happy about the separation into the 3 individual pieces? Right. Can I just dot that one, because it's pretty obvious what the bits are. You finish it off. Now, if you'd left this question as is, and you try to describe the entire surface in X, Y, and Z, can you imagine how ugly that would look? There'd be lots of square roots of X squared minus Y squared minus 4s. It wouldn't end well, right? It just would not be nice. But boom, boom, 3 lines, because there's probably one more line after this, right? And you're done. So it's a version of question 6. We're doing a triple integral over a region I'm going to call E this time. And the equation here is x squared plus y squared dv. And the region that we're interested in lies between x squared plus y squared plus z squared equals 4 and x squared plus y squared plus z squared equals 16. I can't really draw that, but I know what it is. Can you imagine that you had a sphere radius 4, and inside it there was a hole of radius 2? So this region E, right, it's a solid region in 3D space. Isn't it basically a hollow ball bearing? Right. So you kind of visualize that part. So I need to set up what that's going to look like. Well, here goes. The phi is going to be from 0 to pi. The theta is going to be 0 to 2 pi. The rho is going to be 2 to 4. Are you happy where those limits are coming from? The 0 pi and the 0 2 pi. We comfortable where I got those? Right, now x squared plus y squared. Yikes. Okay. It's going to be rho squared, sine squared, cos theta, plus rho squared, sine squared theta squared. And then don't forget, as I was about to, that guy. So it's going to go 0 to pi, 0 to 2 pi, 2 to 4. Try to do as much as I can in one go here. Rho squared, sine squared, cos squared. Rho squared, sine squared, sine squared. If you add them together, don't you get rho squared, sine squared? Agreed? Rho squared, sine squared phi, cos squared theta, plus rho squared, sine squared phi, sine squared theta. Pull out those guys as a common factor. That leaves behind those guys. Don't they get you 1? There. Does it make more sense now? So this mess here is that guy. So it's rho squared, sine squared phi, all squared, followed by a rho squared, a sine phi, then it's d rho, d theta, d phi. You still with me? Okay. I'll just be lazy. That is actually them. I just don't want to write them all the time. This guy is 4 of them, 4 of them, 2 of them, 1 of them, d rho, d theta, d phi. That becomes 6 of those, 5 of those, d rho, d theta, d phi. Another variable separable world. And the outside one is going to be the phi from 0 to pi, is going to have that fella done. The theta is pretty easy because there isn't any. And then the last guy is from 2 to 4 of this fella, right?
Shouldn't it be
To
rho to
the-
the 6th?
What's the 6? Oh, well caught. Right. This guy here is doable. Can I just say ... Just a, what, 1/7 rho to the 7 in some ugly fraction, right? And would you agree this middle one's 2 pi? Ah, we have an issue. And that issue is quite a big one. Out of the 3 variable separables I got, that one was easy, that one was okay, it's just messy, and that one is him. So now we have a separate job. How do you integrate him? Because it's Calc 2 stuff.
That's integration by parts.
No, I wouldn't do it that way.
We can use the fact that sine squared is equal to 1 minus cosine squared.
Okay, let's see that one. Now, I'm not saying integration by parts wouldn't eventually work. I just think it would take you forever and a day to do. But, and I'm taking this quite slowly. But what you said is exactly what we're going to do. So I'm splitting that as 4 of these and 1 of them. And that's going to be sine squared squared. And that's going to be 1 minus cos squared squared. What's this guy? Or how are we going to solve this guy?
U sub.
And won't the u sub be cosine theta? Or phi, I should say. And then 4 or 5 lines later, it's done. Not a short question, right? A lot of stuff to do. But it will eventually come out okay. Are we comfortable with that question now? So I guess what that particular question is telling me is that you got to be good at some trig integrations from time to time. Because polar has a lot of trig in it, doesn't it? Sines and cosines. So you're going to have to integrate sines and cosines, which means you're going to have to be pulling out some Calc 2 stuff. So the version of question 7. Triple integral over E of y squared dv. And they call it a hemisphere. And the equation of this hemisphere is x squared plus y squared plus z squared less than or equal to 9, and that y is greater than or equal to 0. Now, you know, hemisphere just means half a sphere, right? Right, like you take a ball bearing and cut it in half. The orientation of this one is quite interesting. Because if you slice it so that you get a positive y value, right? Then which half do you get? Because if you think about a hemisphere, can you get the top half? Can you get a bottom half? For want of a better word, can you get the right-hand side half? Can you get a left-hand side half? If you make y positive, aren't you getting the hemisphere that is to the right this way? Now that is important because what that's going to allow me to do is to figure out what these fellas are. Now I can do rho 0 to 3. That's because of this, right? When you talk theta, you're talking xy's, right? If you look at this shape, do you see that you're not using? I mean, if you look at it from above, aren't you basically only using? I guess I should have drawn that better. But that's the bit that you're using, right? Right, the positive y values. So what kind of theta makes this happen?
0 to pi.
I guess the last question is, what's phi going to be? Well, think of
Also
phi
0 to
as
pi.
being the up-down kind of rotation. I heard it, I believe I heard it, 0 to pi. So you have to have a visual mind to understand that this becomes that. That makes sense? That this is this is this particular thing. Now, y squared happens just to be an ugly rho squared, sine squared, sine squared. And then we add in, I'm going to make this red because it's going to get crushed in a minute. You're going to do a rho squared, a sine, and then it's d rho, d theta, d phi. So I'll not bother writing that again. These come together and get me 4. This guy comes together with this guy and gets me sine cubed. And this fella here gets me a sine thing. And I have a rho, I have a theta, and I have a phi. Are we happy with this becomes this? Variable separable. And the phi ends up being sine cubed. The theta is actually here for a change. And the rho is what? 0 to 3, or rho to the 4, 0. Well, at least it's variable separable, which is, as you can kind of tell, quite common in these questions. So let's look at how we would do it. This guy, no biggie. Great, power rule. How am I going to do sine cubed?
Take out a sine squared, make that 1 minus cosine squared. Same as the
And
last
then
problem.
u sub it, right? You catch that, guys? How am I going to do sine squared? Since I'm teaching Calc 2, and we're actually in that part of the world right now, do you see a guy in that list in front of you over here that you
Do
could
that,
use?
do sine, cosine, and then u sub.
Sine squared.
Whoops,
Is
yeah, I
it-
was looking at the
yeah.
wrong thing. Turn it into the 1 minus cosine.
Yeah. Well, that would just change the question from how do you get a sine squared to how do you get a cosine squared. So I wouldn't choose that.
I mean the 1/2 times the 1 minus cosine double angle.
Yeah, and off you go and do it. Right. So this guy here, you might want to go sometime in the future, look at this video, just freeze it at that frame and write this down. Have you noticed that we've been using quite a few things from this list today because spherical coordinates tend to generate integrals of sines and cosines of various types. And so you have to be able to know how to do that. And that means you're going to very often have to use identities or u subs in particular to get you out of that. Are we good? So, oops. That we do need this. Last one for today. While I'm getting this one set up, do you want to say hi? So we can do attendance. Okay. Triple integral over a region E of this guy. And this guy is described as being basically a sphere, but a sphere in the first octant. And that means that we're going to have to do the usual problem of what that guy looks like. Right, first octant. Doesn't that make X, Y, and Z are all positive? And if this even vaguely looks right, I'm going to be amazed. Yeah, it didn't look good. Can you imagine you had a quarter of an orange, right? So you took a whole spherical orange, you cut it along the middle, and then you quartered it. So you get this little baby wedge. That's what that shape would look like. Now, on the XY plane, won't you get that guy? I know you have to orientate it differently, right? If you were doing the XY plane, well, let's rewind. Since that is 1, can I go 0 to 1 and get that out of the way? Right, this is for thetas. Theta comes from the XY plane, right? Whatever's happening in the XY plane is what theta is doing. Would you agree 0 to pi upon 2? Phi is to do with the Z plane. So can you imagine I'm on the ground. Don't I just want this piece? So start at 0 and finish also at pi upon 2. Now the guy we've got is an X, which is R sine phi cosine theta. E. Isn't that just rho squared? And then tag in another rho squared sine phi with a whole load of guys I don't have room for. So 0 to pi upon 2, 0 to pi upon 2, 0 to 1, rho cubed, e to the rho squared, sine squared phi, cosine theta, d rho, d theta, d phi. And now split it because it's variable separable. That's this guy. Phi is sine squared. That's this guy. Theta is just a cosine. You happy about the 3 separate regions, 3 separate integrals? All right, let's take each one on its own merits. What method will I use to find this fella's integral? Got you puzzled.
Is it integration by parts?
Integration by parts. Let me think that through. That would go down. That would differentiate. That would go. It would get worse rather than better. After you did one integration by parts, I think you'd have a rho to the 4 e to the rho squared. So no, I will not go that way. Although superficially that would be the normal way to tackle this. It doesn't look like a U sub, does it? It's actually a weird question. It's a U sub followed by an integration by parts. So since I only have time for that one, I'm going to talk through these ones. Isn't that one a baby? Isn't that just sine theta? Isn't that one just turn it into a half 1 minus cosine 2 phi? This is the guy that's going to kill us. The integral from 0 to 1 of rho squared e to the rho squared d rho. And I'm saying
Professor?
use.
It's rho
Yes.
cubed.
Oh, thank you. That's very important. Now, differentiate with respect to rho. Do the crossover and isolate the d rho. So that's the way I do these guys. So this is going to be rho squared e to the u 1 over 2 rho du. The rho's cancel, well, partially cancel, and you get 1/2 rho squared e to the u du. But wait a minute, isn't rho squared u? This guy is an integration by parts. Right?
Wouldn't
This
that just-
guy,
Wouldn't that just be u, not u squared?
let's check. There's a cube. Oh, well, got still an integration by parts, but a lot quicker than it would have been with the u squared.
It wouldn't be rho squared, it would just be rho, right?
This would be
You're dividing by
rho.
rho.
Yeah, this here is a rho cubed. Take out a rho gives you a rho squared. A rho squared becomes a u.
I see now.
And this is an integration by parts. And some of you do UDV method. I don't like it, but that's fine. You can do it. It works perfectly fine. I would call this guy f of u, and I'd call this guy g of u. And 5 minutes later, I'd get the answer. And whatever it is, evaluate it at 0 and 1. Eventually, anyway, you get this. Get that guy, multiply the whole mess together, and you'd be finished. And that got us to question 8, which is not bad, which is